let's get started with our main discussion about a new chapter, a very important technique about knowledge distillation, which is a very effective technique widely used in industry these days to shrink the neural nets to fit tiny devices. So today we will learn several topics, including what is knowledge distillation? Okay? How do we have a teacher model? What is a student model? And how do we transfer the knowledge in a neural network from the teacher model to the student model? Okay? And we also want to learn what to match. Okay? What is the distillation? What are the things we want to learn from the teacher model? And then we want to learn about this self and online distillation. Okay, and distillation for different tasks, including detection, segmentation, etc. Finally, we'll talk about network augmentation, which is a training technique for tiny machine learning models. Okay. All right, so what is knowledge distillation? So nowadays, we have both cloud AI and also tiny AI, right? So for cloud AI, we can have a huge amount of computation power, like tens of teraflops per second of computation, tens of gigabytes of GPU memory, right? However, on a tiny device, like a microcontroller, an IoT device, the computational budget is very limited, right? We only have a few million flops per second and a couple of hundred kilobytes of SRAM. So the models that are designed for cloud AI may not fit those tiny devices, right, due to the tight memory constraint. Similarly, for the neural nets, we used to have these pretty large neural nets like ResNet, VIT. For tiny devices, we will have these smaller neural nets like MCUNet, MobileNet Tiny, right? So we want to distill the knowledge from these large cloud-based models to these small edge AI models. Okay. Otherwise, we will observe this significant difference of accuracy between this cloud model. Like this is the training curve for less than 50, right? So with the increasing amount of training epochs, we can see the accuracy. This is the training accuracy. This is the validation accuracy. We can train the model. The training accuracy can almost reach more than 80% accuracy, right? However, on this MobileNet Tiny, a much smaller neural net, the accuracy is much lower, okay? Only 52%. So that's reasonable, right? We have a much smaller capacity, a much smaller hardware resource. Then, of course, the accuracy for such tiny model is a lot weaker than those cloud-based models, right? So here, knowledge distillation, the main target is basically to distill the knowledge for the models that are large, that are powerful, to the models that are small, that are tiny, that require low computational resources. Okay. So with that, knowledge distillation is a very popular technique. Was published in 2015 and already has more than 10,000 citations. Okay. It's a very simple yet effective method to transfer the knowledge from the teacher network to the student network. Okay? This could be a large model you train on the cloud. This could be a smaller model you want to deploy on a microcontroller, on a Raspberry Pi, on an embedded device. Okay? And here we have the basic idea about knowledge distillation, right? So we have an input. It could be an image. It could be a natural language. It could be speech. And then we pass it through both the teacher network and also the student network. And then we get the prediction logics, okay? And for just training the neural network, we used to have this classification loss if we want to do an image classification, right? But now we have a new loss, okay, called distillation loss, which try to match the logics produced by the teacher model and the student model. Okay? We try to learn from the teacher, okay, by trying to match their logics. So that's why we have a new loss called the distillation loss. For example, we are given an input image, a cat, okay, and passing it through the teacher model and also the student model. Okay? Student network could be much smaller than the teacher model. Okay? And here we are doing a binary classification between cat and dog. Okay? So the logics from this teacher model is 5 for the cat, 1 for the dog. So of course we have higher probability that this is a cat, right? And we calculate the probability by calculating the softmax. Right? We have learned that by calculating the softmax of these logics, we will get the probability that the teacher model thinks 98% of the percentage we think this is a cat. Okay, very confident, 98%, versus there's 1.7% probability that this is a dog. Okay? On the other side, the student model's prediction is different, right? So the logics are smoother, like 5 versus 1 versus 3 versus 2. Okay? After calculating the probability, okay, so we find the probability of where the student model think this is a cat, the probability is only 73%, okay, versus the student model thinks there are about 27% probability that this is actually a dog, right? Showing that the student model is actually less confident given this input image. Okay? So during the in the cross entropy loss, okay, we just think this is already a correct prediction since the probability for the cat is higher than the dog, right? Then we are going to classify this as a cat, right? However, this is not enough, right? The confidence for the student model is actually different from the teacher's model, right? That's why it is helpful to not only match the correct class, okay, but also try to match the logics, okay? Try to match the logics of the teacher model and the logics produced by the student model, okay? Let me give a pause, make sure everyone here understands the motivation and how distillation works. Okay, very good. So here we want to bump up the probability for the teacher-student model for the cat, right? And decrease the probability for the dog. Okay? This cannot be achieved by just using the cross entropy loss, since cross entropy loss just penalize the wrong prediction, but actually this is a correct prediction, just it's not as confident. So we also have the concept of temperature, right? So what is a temperature? So if the temperature is 1, we are just dividing each logis by 1 and then calculate the softmax. So if we add another temperature, say a temperature of 10, we are actually dividing the logis by the temperature to further smooth the probability, right? So if we apply a temperature of 10, then rather than 98%, then it becomes about 59.9% of probability that the teacher model thinks this is a cat, right? So in reality, when we are trying to match the logics of the teacher model versus the logics of the student model, we usually apply a temperature that is larger than 1 to smooth the prediction. So having talked about those intuitions, let's formulate it in math to see what exactly are we trying to match in the knowledge distillation. So we have the teacher model, we have the student model, and this is T is the temperature, okay, and Zi is the logics for class I. Okay, so we calculate the softmax of the different classes, okay, where C is the number of classes and T is the temperature, which is normally set to 1. Okay, and the goal of knowledge distillation is to align the class probability distributions between the teacher model and the student model. Okay, all right, just like what we showed in the image before, if the student model is less confident, by learning the logics from the teacher model, it's going to be more confident, right? So further, we are going to discuss a couple of topics. What are we trying to match between the teacher model and the student model? Okay. Of course, the simplest match is basically the output logics. Okay, so we are given an input. Teacher model has several layers. Student model also have several layers. We are trying to match the output logics. Okay, we try to penalize the difference between the logics of the student versus the logics of the teacher. So here we can either use the cross entropy loss, okay, a minus p log p student, this is p teacher. Okay, we can also use the L2 loss, okay, calculate the L2 distance between the teacher and the student. Okay, very intuitive and very easy to calculate the gradient. We can also try to match the intermediate weights and intermediate features. Okay, so rather than matching the final prediction, we can also match those intermediate weights or intermediate feature maps. Okay, for example, like layer 1 of the teacher match the layer 1 of the student. Layer 2 of the teacher match the layer 2 of the student. Okay, this could be the weight, could be the activation, it could also be the gradient. And we are going to see them separately. So this is one of the approach that is trying to match the intermediate gradients, intermediate weights. Okay, let me move this zoom so that you can see the citation on the bottom. Okay, so other than this cross entropy distillation loss, okay, we can add this L2 loss between the teacher's weight and the student's weight. Okay, so usually the student model will be smaller, have a smaller dimension than the teacher model, right? Therefore, we need a projection, which is usually a linear layer, okay, that projects the weight tensor of the student model to the same dimension as the teacher model, okay, so that we can calculate the L2 distance between the teacher model's weight and also the student model's weight. Okay, so this is matching the intermediate weights by adding this FC layer to align the shapes of the teacher model and the student model's weights. We can also try to match the intermediate features. Okay, imagine basically a neural net is a automatic feature extractor, right? So the features extracted by the teacher model should be very similar to the features extracted by the student model. So here we are trying to align the feature between the teacher model and the student model. Okay? So rather than this is before matching, this is after matching. Okay, but we can hardly tell the difference between the features generated by the teacher model versus the features generated by the student model. Okay? And here we are minimizing this maximum mean discrepancy between the feature maps. And this is the way to calculate this distance, which is basically calculating the cosine distance. Okay, so this is the feature map of the teacher, feature map of the student, and these are the cross terms between the teacher and the student. Okay, so the closer the feature maps, the larger this term. Since there's a minus sign here, the smaller this loss function, right? So the intuition is that if two vectors, if they are very similar, then the cosine distance will be very small. Then the loss will be small. Okay? We try to penalize such difference. Right? This difference, and this is very similar. Okay? Try to match the intermediate feature maps. There's another way, try to minimize the L2 distance between the feature maps. Okay? So the teacher network produces a feature map. The student network also produces a feature map. Okay? For the teacher model, we first squeeze the number of channels from M channels to M times K channels. So typically K equal to 0.5, right? To and then we try to reconstruct this feature map by another linear layer, trying to project it to M channels. So this is acting like a autoencoder, right? And here we try to match the L2 distance between these two feature maps. Okay, the feature maps generated by the teacher network versus the feature map generated by the student network. All right, question?
I was confused. Why did we change the dimension?
So here it formulates something like autoencoder. We first decrease the channels and then increase the channel and try to make these two feature maps match.
Is it because the feature map of the student network
So it is hidden by the zoom. So let me move away this bar. So oh, it's still shadowed by the zoom. So actually they are different. And we try to make sure the channels after this projection match each other. The teacher model may have a smaller number of channels. This may have a large number of channels. So we shrink the number of channels. Here we also transform the channels, make sure these two feature map matches each other in their dimensions. Okay? And also so that they can calculate the output distance with each other.
But those features are not necessarily create the label at the end, just in the middle.
Yeah, they are just in the middle. They are not the final features. Actually, there are different ways, right? So this just gives you some insight where you can do these complicated transformations. You can also do some simple matching, right? For example, you can just use one linear layer to project the teacher model to the same dimension as the student model and directly match them, rather than using this complicated autoencoder. All right. So we talk about intermediate weights, matching intermediate features. How about intermediate gradients? Okay. We want to match the gradient produced from the teacher model versus the gradients produced by the student model. Okay. So actually, the gradient with respect to the feature map is also called the attention, right? So basically, the attention of a scene feature map is basically d loss over d activation, right? So if we change the input, or if we change this intermediate activation by 1 unit, okay, how much will the output change? So that's this d loss over dx, right? So if we change, if the change is very large, it's showing that this region matters a lot to the prediction, okay? Versus some areas, if you perturb it a little bit, the output will not be affected, right? It's showing that this region probably is not quite important, right? So here, that's why we are using this attention map. Just by using this d loss over dx, we call it the attention map. And here we are trying to match this attention map between the teacher model and the student model.
That's the attention map is for a specific input, right? Like it's only for this one picture of the wolf that this attention map is valid. Like maybe there's a different picture of a different wolf. And
of course, different input, the attention map will be completely different. And here we are matching, given the same input, the teacher versus the student model should produce the same attention map. For example, here is the teacher model, which is deeper. Okay, this is the student model, which is shallower. Okay, so when we have the same resolution, so here we try to calculate this attention loss, okay, which is basically the L2 distance between the student attention map, okay, versus the teacher attention map. Okay, and we want to make sure they have the same resolution, so we can directly subtract them, calculate the distance, right? So make sure they are in the same stage and resolution. And there's also this interesting observation that a performant model like ResNet, okay, versus a weaker model, which is network in network. This is a much older model, has only 62% accuracy, versus these better ResNet models has more than 70% top-line accuracy. Given the same input, okay, if we would try to distill the student model using these teacher models, okay, which has higher accuracy, we find these teacher models roughly have similar attention map, okay, versus the student model here has a different attention map compared with these two teacher models. Okay, so the attention maps of these performant ImageNet models are quite similar to each other, but less performant model has quite different attention maps. Okay, and here we are trying to match the attention maps between the teacher model versus the student model. All right, so far we talk about the simple method, just match the output, versus we can match these intermediate layers weights, intermediate layers features, intermediate layers gradients, also called attentions, right? There's another thing we can match, right? Think about the activation function we use in vision models. We use this ReLU function, right? So what is ReLU function? If the activation is greater or equal than 0, then it is whatever it is. Otherwise, it becomes 0, right? It will be the neuron will be dead. So it naturally makes the output very sparse. Okay? Some of them are 0 after ReLU. Some of them are non-zero. And here, by distillation, we are trying to match this sparsity pattern. Okay? So basically, a neuron is activated after the ReLU if the value is larger than 0. Okay? So we have an indicator. If x is 0, then it's 1. Otherwise, it is 0. So here we are trying to match this sparsity map. Like this, the activated region, all the numbers are below 0. So after ReLU, it becomes 0. So these are the activated region, which are positive. Okay? So by teacher and student matching, we try to match this sparsity pattern. Okay? So what's the difference between matching the sparsity pattern versus matching the feature map? So here we don't care the number, the difference, but we just care about whether they are positive or negative, right? We just care about the sparsity, if it is 0 or non-zero. Okay, no matter if how large it is, as long as it is larger than 0, then we think they're similar. Okay, it's more relaxed compared with matching the entire feature map. Okay. All right. So far with all these matching techniques are trying to map individual neural nets, individual images, right? So now we try to match some relational information. Okay. So this is quite new. It will be quite interesting. Here we have this teacher model. We have this student model. Okay. So previously we are just matching those in activation one by one, right? This activation versus here, this activation versus this activation. But actually, we can also match the relationship between picking two locations at the same time, right? From the output of the stage 1 versus the output after this residual module, we put them together and match that of the teacher model. Okay, so here we use this inner product to extract those relational information. Okay, which is a matrix of C in times C out. Okay, for both the teacher and the student. This is different from the conventional method where we just match individual points. But here we are matching from layer I to layer J. We are trying to match their relationships. We think the teacher model and student model should have this similar relationship among two different locations in the same neural net. Okay, so previously we also just match given the same image, like you mentioned, try to match the teacher model versus the student model. And given a second image, we try to match them again. What about we have multiple images and their relationship, right? So rather than just trying to match the student with the teacher for image 1, image 2, image 3, try to match them individually, we allow some difference between them, but we try to make their relationship try to match the 1, 2, 3, 1, 2, 3, trying to match the relative relationship rather than putting the student exactly to the same location as the teacher. Okay, so this is the difference between the conventional knowledge distillation versus this relational distillation. So here in the relational distillation, given different inputs, so here we have n inputs producing n intermediate feature maps. Okay? So rather than matching feature maps one by one for n different inputs, we are actually mapping first calculating the relationship between these n images output, right? So here we calculate the distance, picking. So here we have n outputs. Okay, so how many relations are there? How many pairs are there? So n times n minus 1 divided by 2, right? So we have this amount of pairs, and we calculate the distance of each of them, okay? And we use this L2 distance to denote this relationship between the outputs of n images, okay? So that gives us a tensor, which is RT. The dimension, the vector's dimension is basically n times n minus 1 divided by 2, since we have this amount of number of pairs. Okay? And we are trying to match the distance between the teacher and the student model by using such pairs. Okay, so this is about this relational knowledge distillation. People have tried that on several data sets and find it's quite helpful. All right, so far we talk about this teacher model, we talk about this student model, right? You have to have a teacher model to begin with. What about you learn on yourself? Okay, so people as students, we can learn ourselves without any teacher. So how about neural nets? Can we make distillation teacher-student model without having a teacher to begin with? So we introduce self-distillation, and then online distillation, and then combine the distillation. Okay, that would be very cool. So to continue giving some context, teacher model usually larger than the student model. We have to train this teacher model to begin with and fix it, and then it produces the logics. When the student is being trained, we try to match these two logics. So what is the disadvantage of this fixed large teacher model? First, we have to pay this training overhead, right? In order to produce a smaller model, we have to first train a much larger model to begin with, right? So there's training overhead, and also it takes memory to store those logics, even if you do it online, right? So the goal is, can we just have the same architecture without having to train a much bigger model to begin with? So this work is very interesting, called self-distillation with born-again neural nets. So what is a born-again neural net? So you start with some neural networks. So here we have a teacher model, and here we have the correct label. Okay, so given x, we pass it to this teacher model, and we get fx. Okay, and we have the ground truth, which is y, and we use this y to supervise this fx, right? And then we use this teacher to train a student model. Okay, so the teacher model and student model actually they have this very exactly the same architecture, right? So the network architecture for the teacher and student are exactly the same. This is not a bigger model than the student model, but they have exactly the same architecture. We use the teacher model to supervise the student model. Okay, they share the same architecture, but not the weights. Okay? So after one generation, we get one student model. Okay? And after that, we use the first generation of student model to distill the second generation of a student model to get the grandchildren of this teacher model. Okay? So we do this many generations, so until we get a k student models. Okay, we use s student k minus 1 to distill student k, right? So here is showing what we are distilling. So after that, we get a whole generation, a whole family of neural nets that have the same neural network architecture, right? So this is like the grandpa, this is the father, and this is the child, right? So what about at the prediction time? What do we do? So we have k different student models. They are trained sequentially one by one, right? And we can get each prediction one by one. Finally, we are going to do an ensemble, okay, to have the average of their predictions. Okay? And the research from this paper is finding that the natural accuracy is getting better and better with the teacher, the first generation of student, second generation of student, until the kth generation of student.
Why do an ensemble and not just use the last student if the accuracy is just increasing all the time?
Yeah, usually ensemble of many neural nets will have a higher accuracy than each of them individually. But if you have limited computational resource, of course, you can just use the last one to run inference individually. Of course, doing such ensemble, the computation flops cost is k times individual inference, right? So that's why we are saying here we can alternatively ensemble them, or we can just use this SK individually to perform the inference.
What is the intuition behind why it's improving in each iteration? Because isn't it like the student is actually sort of being pressured to like look more like the teacher to like be more accurate? So why is it getting more accurate?
So here we are usually a neural net if you train it longer, right? So here we get a more fine-grained supervision, not just this hard labels, right? If you have hard label, say cat, dog versus an elephant, right? If it's a cat, then both dog and elephant you have zero probability in the ground truth. But one image maybe might be something closer to a dog, which such hard label cannot really tell. But this is just doing finer and finer grained of supervision to give you the soft labels from one generation to another to gradually extract those knowledge.
Is there any like theory behind this, or is this just
entirely just experimental, right? Including the original distillation paper, I think this is very just experimental knowledge.
A quick follow-up on that. Is there any situation where it doesn't work so well, like any type of problem that you're trying to solve, or type of data, or
what type of data does not work well with distillation? There are several problems where it is hard to distill. For example, later we will talk about regression tasks rather than classification tasks, and we will learn how to convert those like regression tasks, which is difficult to find the probability distribution, into a classification task, so you can actually try to match the distribution.
So, for example, in the step 0, the fx is yet a neural network.
Yeah, so x is input, t is the neural net, teacher is the input, fx is the output.
But y is the label.
Y is the label and used to supervise the result. So fx is the result from x after this model.
Mm-hmm. And then in the step 1, is S1 initialized randomly, and then tries to learn the same fx?
Yes, S1 is initial randomly, and T is pre-trained.
But it's still trying to learn fx from T, right? No. What is the distillation loss?
So here we are trying to match the output logics, right? So that's the first loss. The second loss is just the cross entropy loss compared with the ground truth. Is that clear? Yeah. Okay. Yeah, I'm not quite aware of other scenarios where it fails, but maybe you can try that for the final product. It could be something fun. All right. So that's about self-distillation, right? And then we're also going to talk about online distillation. So rather than having to train a model to get a fully pre-trained model, okay, now we can have two models initialized from scratch at the same time. None of them is a teacher, right? They're just two students sitting in the same classroom trying to learn from not only the ground truth, but also learning from each other, right? So apart from the ground truth, they're also supervised by minimizing the KL divergence about between the probability of each other, right? So the network 1 and network 2, they can be the same architecture. They can also have very different architectures. Okay, so we just want to add a distillation objective that minimizes the output distribution of the other party. Okay, so for student and for the teacher, they both have this cross entropy loss with respect to the output ground truth versus this KL minimizing the KL divergence between the student model's prediction and teacher model's prediction given the same input. Okay? So they are trained from scratch. They learn from each other. They also learn from the ground truth. Okay? So this is the online distillation called deep mutual learning. They are learning from each other. So here they have some comparison in the paper. Independent learning versus deep mutual learning. Okay, this is net 1, net 2's accuracy. Okay, so can be either the same, both ResNet, can be different models, can be MobileNet versus ResNet. Okay, and this is deep mutual learning's accuracy subtracts the individual learning. So we can see they are consistently positive, which is pretty interesting, showing that such deep mutual learning is better, showing better results compared with individually. But this is on the small CIFAR data set. So on large scale data sets, it remains interesting to see the effect of such online learning and mutual learning. Okay. Okay, let's continue talk about how about we combine them together, right? So I'm going to introduce this on the fly, okay, native ensemble as the teacher network. Okay. So the idea is basically to generate multiple outputs, 1, 2, 3 output probability distributions, and ensemble them together. Okay, ensemble them together as the target distribution. Okay, for the knowledge distillation. So we are using the result prediction of each other to ensemble them together. Say we can average and get the mean of them to get this on-the-fly knowledge distillation, and we use this mean to supervise each probability, each prediction individually, right? Okay, so here we are adding more parallel branches to the backbone, and each branch is going to make a prediction here in gray, right? And we have a gate which is used for ensembling the logics from different branches. Okay, and here we are finally using the ensembled probability distribution to supervise the prediction of each branch, branch 0, branch 1, branch n. Okay, so similar to deep mutual learning, this one method allows the teacher model to be exactly the same as the student model. So here we don't have any explicit teacher model. Teacher model and student model, they are inherently the same. Okay, it doesn't require any pre-training. Okay, everything is just trained from scratch. We don't have to train a teacher model to begin with. This is basically learning from myself on the fly. Okay, it's also not necessary to train two models as deep mutual learning. We are just learning one single model rather than in deep mutual learning. Even if we want to just obtain one model, we have to train two models in parallel, right? And here is showing the result of this on-the-fly native ensemble method. So on top of baseline networks, it consistently improved the error rate on ImageNet, and also compared with this deep mutual learning, where you have to train two models. Now you just have to train one model. Okay, the accuracy is consistently lower. This is showing the error is consistently lower. And finally, we can combine this online and also this self-distillation. Right? So here we have several res blocks. Okay, so shallower layer versus deeper layers. Okay, so usually we can have more confident prediction as we enter this later layer. But for some input examples, which are very simple inputs, we don't have to go through all the layers, but maybe after ResNet block 1, we can get a prediction that we are quite confident. Maybe it's already good enough. We don't have to run inference for other res blocks. Okay? And also we can use these deeper layers to supervise those shallower layers, right? So again, you are teaching yourself. We just have one neural network model. We don't have to have a separate teacher model, a separate student model, but just one model, okay? And we are learning on the fly. We are using the later layers prediction to supervise these earlier layers, okay? So this is showing the trade-off between accuracy and acceleration, right? If we can exit after res block 1, right, the acceleration is fantastic. We don't have to run the future layers, just finish the first block. So it's much faster, but accuracy is lower, right? We just go through the one layer, we try to make a prediction. Versus if we go to deeper, the accuracy increases, but the acceleration will decrease, right? So if we can use those deeper layers to supervise those shallower layers, okay, in the end, hopefully the shallow layer itself can make a good and reliable predictions without running the whole stage. Okay, and as a result, this is showing on different neural net architectures, VGG, ResNet, wide ResNet, etc. And this is a baseline accuracy, right? And here we have running only 1 quarter, 2 quarters, 3 quarter, 4 quarter versus ensemble these 4 different subnets together. Okay, and the red part is showing this part output. It's weaker than the baseline. Okay, and for if we run through 2 quarters, half of the model, several scenarios like this one, and the first one is already outperforming the baseline model using this deeper layers to supervise deeper layers like this to supervise these shallower layers. Okay, and if you run through 3 quarters of the whole network, only one model is weaker than this baseline, and it's not a lot weaker. But all these other remaining models is actually already showing better results than the original baseline model, right? And for running the whole model, it consistently outperforms this baseline, not to mention ensembling different 4 outputs together. Okay. So this is again CIFAR 100 results. ImageNet result will be much more convincing. All right, so far we talk about different locations to run the distillation, either the output logics, or we match the gradient, we match the input activations, we match the weight. Okay, we can also match the relationship between different parts of the net versus different images. We also talk about without a teacher model, just online self-distillation. All right, let's resume to continue discuss about distillation for more applications beyond classification, right? For example, object detection is a very critical application for mobile and edge AI, like autonomous driving. They all require accurate object detection. So here we have the backbone, and also we have the detection heads. And here we have the teacher and the student. So for the backbone, basically the distillation is trying to match those intermediate activations. So there's the only new part is probably just try to match the number of channels, the shape, right? For example, student network can have much less number of channels compared with the teacher model. Therefore, we adapt it by using one-by-one convolution to match the shape. So we can directly calculate the distance between the feature map of the teacher versus the feature map of the student. But the true different thing compared with classification is here on the detection head. So here we have the detection head giving both the classification and also the regression for the class and also the bounding box. Okay, so classification is providing the class, and the regression is giving the bounding box, right? So for the bounding box, let me move away my zoom so that you can see the equations here. So we use different weights for foreground and background, right, to handle this class imbalance problem. So the class for foreground and background is quite imbalanced. There's a lot of imbalance. So here we give a term weighted. So here we are calculating the weighted p log p, which give a different weight for the foreground and background, right? So to penalize them using different weights. Okay, so weighted cross entropy loss for the classification for the foreground and background. And also for the bounding box regression, we have to regress the bounding box for different objects, right? We are going to give 4 real numbers, xy for here and xy for here, right? So here we want to exploit teacher's prediction as the upper bound, okay, for the student to achieve. So once the quality of the student surpasses that of the teacher with a certain margin, so here we give it a certain margin, which is denoted by m here. Okay, so when the distance between the ground truth versus the prediction, do we hope it larger or smaller? Smaller, right? We want to try to match the gradient, try to match the output with the ground truth, right? But initially, the distance might be quite large. So as soon as the distance it's plus m plus this threshold is greater than this number, okay? So initially this could be pretty large, right? As soon as it is small enough, right? So we don't give in any penalty, right? Otherwise, we have to continue penalize that until this one is smaller or equal to that of the teacher, right? So this is another thing that is different from classification.
What is the intuition? Why did they put that?
This is the basic intuition is that we don't penalize all the way, right? So as soon as the student is good enough, we don't add this loss anymore.
Then I have one more question. What is weight imbalancing? You said in the last slide.
Oh, last slide, the foreground versus background classes. Okay, a lot of predictions could be just uninteresting background classes versus just a few interesting classes, which are foreground classes. So you want to give so for example, you want to take a picture of your friend. The person is the foreground, and the remaining stuff is the background. And you want to have different weight for the foreground versus the background.
Oh, for loss.
For the loss, yeah. Otherwise, you have too much background. And another different thing is the just now asked a question: when does distillation does not work, right? When distillation does not work. So bounding box regression, you have to give a real number, right? The xy location for this point, the xy location for this point. But all the losses we talk about are talking about classification tasks. We have a distribution among different classes, right? But this is a regression problem that's totally different. So how do we get around with that? Actually, we can turn this, convert this bounding box regression problem into a classification problem, right? We can discretize the x and y grades, right? For example, for y location, we want to predict the ground truth is actually we are in class 2, right? 1, 2, 3, 4, 5, 6. We are in the second class, showing that we are in this row. And for the column wise, we can also discretize that, right? And convert this regression problem into a classification problem. Right? So the more number of grids, the more accurate it is, but also the more computation, right? So question here.
You're using like a picture with a finite number of pixels. Isn't it already a classification problem if you're just trying to put the box aligned up with
It is already a classification problem, but the resolution is so high that you may have a lot of computation to do such fine-grained prediction. All right, so that's how we convert the regression problem into a classification problem. So we can try to match the distribution among different probability distribution among different classes, try to reduce this distillation loss. Okay, so that's something special for object detection. Another important task is semantic segmentation, right? Given a picture, we want to segment which part is the drivable region, which part is the pedestrian walkway, which part is which part is the not drivable trees and grasses, right? So apart from this similarity map, this feature imitation, which is very similar to this classification tasks, okay? So actually we add a new network, which is a discriminator network, okay, to produce this the adversarial loss, okay, for the teacher net, for the student net, okay, and we give two different masks, okay. So this is pixel-wise prediction. So each location we have to tell whether this is road, whether this is drivable, whether this is tree, right? So we have two masks, and we want to have this discriminator net, okay. For real image, we have a real embedding. For the student model, we call it a fake embedding, okay. And we try to match the distance and also try to train a discriminator to try to distinguish whether this is real or fake. Actually, trying to tell whether it's from the teacher or it's from the student, right? We are trying to improve the student model, and so that the discriminator cannot tell it's actually generated by the student model, okay? And also we are trying to train this discriminator, trying to find, okay, whether it's produced by the teacher model or the student model. So the discriminator and the student net is getting better on top of each other, so that in the end, the student model will generate very high quality feature maps, prediction maps, okay, that is very similar to the teacher model. Okay, so that's difference for segmentation. And also in 2019, we published this paper called GAN compression. We also use knowledge distillation to compress the GAN models, right? So we have a pre-trained teacher generator. Okay, we are trying to distill a student generator. Okay, so here we are combining that with the once for all technique with training the supernet, right? So we can train 1/4 of the channels or 3/4 or half of the channels. Okay, and here we are trying to match those intermediate feature maps by using this distillation among the intermediate feature maps, right? And since we are using this once for all technique, we may have an elastic number of channels. So here we are using a 1-by-1 convolution to project from the student to the teacher so that we can directly calculate the L2 distance between the feature maps, right? So here we have smaller number of student channels. That's why we are using a smaller 1-by-1 convolution to project. Here we have more student layers, channels. So you are having a larger amount of layers as channels as input and same amount of channels as output, so that we can directly subtract these two feature maps. Okay. So altogether we have 3 loss. So reconstruction loss. Okay. Try to minimize the distance. So here we are turning a horse to a zebra, right? So the student model get a zebra. This is the ground truth. We try to minimize this reconstruction loss. And also we are trying to minimize this distillation loss, try to match the intermediate feature maps. And also we have this conditional GAN loss like before. Okay. And we use these 3 loss functions to train it together. And as a result, we can turn a horse to a zebra in very low latency, in real time. Right? So this is measured on this NVIDIA Jetson Xavier GPU, which is a mobile GPU. Previously, it runs about 12 frames per second. You see, it's very slow. But after such optimization, it can run at about 40 frames per second. So it's 3.3 times faster. Okay, and the FID is larger than the previous model, and the flops is reduced from 56 gigaops to only 3.5 gigaops. That's 16 times reduction, right? Much faster. With better kernel optimization, we believe there's a lot more room of optimization, right? So let's see it again, from slow to fast, and also the quality is well maintained. This is another demo using GAN compression to turn these sketches into shoes. Okay, you can erase. You can previously it is pretty slow. Okay, 1.6 frames per second. Now it's more responsive. You can draw a Nike logo, and there you have a Nike shoe. Previously, it's not very interactive, running only 1.6 frames per second, versus now it's about 4 frames per second, and this is running on very low-end Jetson Nano, very low power edge device. All right. This knowledge distillation also works for natural language processing. Okay, we can transfer we can try to match those intermediate feature maps. Okay, and in addition to that, we can also try to mimic the teacher model's attention. Right. So attention layer, you have a n by d QKV query key and value, and you calculate the attention map, which is n by n. We are trying to match the attention map between the teacher and the student. We haven't talked about the architecture of transformer yet, but we're going to cover that in later lecture. So here we have a special layer called the attention layer. So here we are trying to match that attention layer as well as this intermediate feature maps. All right, so we talk about many different applications. So let's switch gears to talk about network augmentation, right? Another technique complementary to distillation, but very similar to distillation, targeting improving the accuracy of small and tiny neural nets to prevent underfitting. So conventional approach, we have this data augmentation, which is widely used during training to avoid overfitting. So one image can become many images. For example, we can do cut out a certain region in the image. We can also do mix up. So we have a cat and a dog, and we mix them together to get a cat dog, and then have a probability of 0.5 for each. Okay, so that's mix up. We also have this, people also propose this auto augment, right? So one image can become many images for different batches using different policies. You can tilt it, you can rotate it, you can also tint the color differently, right? So this is data augmentation. People also have these drop-out techniques to prevent overfitting. You can remove nodes, and also you can drop out certain channels. You can also drop certain blocks, right? So all these techniques, either data augmentation or dropout, can improve the neural network's performance, right? This is a baseline model, which is less than 50. By using mix-up, auto-augment, drop block, the accuracy is keep increasing, since that prevents overfitting. However, if we use those techniques like mix-up, auto-augment, or drop blocks for this tiny model, like Mobile V2 Tiny, which has only 23 million max compared with 4 gigamax, okay? The accuracy actually hurts a lot by using these techniques, right? So all these techniques are targeting preventing overfitting, but such model is already super tiny, super small. It doesn't suffer from overfitting problems, so you shouldn't continue augmenting the data, but instead you should augment the neural net. So that comes this network augmentation technique that try to augment the neural network and provide more capacity and give extra supervision during training for those tiny models. Okay? And by using this network augmentation, we can actually drastically boost the performance of such tiny models compared with the baseline. And how does that work? So we are given a tiny neural network. We have an input. We'll calculate the loss using the weight, okay, to backpropagation. The network is very small. It has very limited capacity. So what we want to do is actually build an augmented model. Okay, let me move the bar up so you can see everything more clearly. So we are going to build an augmented model. They share the weights with this tiny model. Okay, you see the red region. These weights are exactly inherited from this base child, this base original tiny model. Okay, so we just expanded the number of channels, okay, for each layer, and then we use the original weights for those shared layers, shared weights. Okay, so during training, for each step, we are going to do forward on the original model, backward, and forward, backward also on this augmented model. Okay, so this weight not only acts as a weight in this neural net, but also acts as a weight in this neural net. It's going to get two copies of gradient, one from the base model, one from this augmented model. Okay, we are going to sum them up together for these two gradients. To sum them up using this alpha to control the ratio to get some auxiliary supervision besides this base supervision. And during each training step, we can choose different subnetworks to augment different methods to augment the original network. Okay, the base model stays the same. Okay, so different iterations, we are using different different superset of this model, very similar to the Westphal network. Okay, to give extra supervision for the base network. So after the result, we can find after several epochs of training with NetAug, the training accuracy and the validation accuracy both increased from blue to red. Okay, so this is the mobile V2 Tiny, and I believe this is the ImageNet dataset. Okay, so the validation accuracy actually improved more than the training accuracy, right? Showing it's very healthy. Compared with a larger model like the ResNet, okay, the training accuracy did increase, but actually the validation accuracy is lower, right? Showing that it's suffering from overfitting, right? So these tiny models should really prevent it from underfitting. So that's why we are using NetAug for these tiny models to give some extra capacity and some extra supervision, not for those already big models. Question?
Sorry, the weights that you added as augmentation are in random weights?
These are random weights. Okay, so these are random weights. These weights are shared. These are not. These are shared from this one.
Together, the same way throughout the training.
Throughout the training, both this red one and this black one are going to be updated at the same time.
No, I mean the red one on the right and the left, they're going to change also at the same time, the same way.
This one and these weights?
No.
Black one or red one? This one and this one? Yeah, they are lockstep. They are always the same during each iteration of the training. They are always shared. So the update, they have two terms. One comes from this G base, one comes from this G aug. So the weight update will consider both updates, and they're always shared.
What is the intuition? What happened that someone came up with it?
So the idea is that if you have only your one neural network, it's going to get very limited supervision just from this single model, right? But you want to put it yourself in the context of a larger model. Hopefully, if you get stuck in a local minimum, some other capacity, some other parameters to give you more degree of freedom to prevent you get stuck in the local minimum. And suddenly you get extra, say you are stuck in the saddle point, and suddenly you get another degree of freedom, so you can continue go to a lower optimal place. But at inference time, we get rid of those extra capacity and extra parameters. Very good question. And we are finding actually this is for different neural nets measured on the ImageNet dataset. And this is the baseline model, knowledge distillation itself. network augmentation plus knowledge distillation. This is actually different from knowledge distillation, where we don't have a teacher model and a student model. We just have one model, right? We can augment it, right? And it's actually performing better than knowledge distillation and can be combined with knowledge distillation. Also works quite well for transfer learning into many different subtasks. Okay, so compared with just training it longer, the network augmentation can help boosting the performance of transfer learning on different tasks like food, flowers, cars, etc. Not only on classification, but also on detection. We can improve the accuracy and also showing that it's the same as reducing the number of max to achieve the same accuracy. Okay, in summary, today we talk about knowledge distillation, targeting using a teacher network to improve the accuracy and performance of a student network. Okay, we talk about different places to distill. Okay, we can match the gradient, match the activation, match the final logits, match the intermediate activations, and match the relationships, right? And also solve an online distillation without a teacher. It's just learn by yourself without training many different models. Just keep improving a single model or use a deeper layer to supervise shallower layers. Okay, we talk about KD for different tasks. Beyond classification, we talk about detection, segmentation, GAN models, and also NLP tasks. Finally, we talk about network augmentation. Rather than augmenting the image, augmenting the data set, we augment the network for to prevent underfitting, okay, for tiny models. In next lecture will be an exciting lecture. We are going to introduce MCUNet, which we already have enough knowledge to do a system design, right? To do a real world design given a tight resource budget, only 256 kilobyte of memory. Okay, you are going to experience that in lab 4. Okay, so system algorithm co-design framework for TinyML on microcontrollers. And also we're going to distribute those microcontrollers and cameras to every student, right? So make sure in the coming few lectures you come to the classroom to bring home those boards. Okay, you can take it for this entire semester. Okay, all right, that's all for today's lecture. Thank you, and have a good weekend.